All right, guys. Can you guys hear me? Okay, guys.
Yes.
You guys hear me? Perfect.
Yep.
All right. So welcome, guys. Welcome to our AlexIvySchool, 常春藤双语讲堂. We are an educational organization which provides extensive trainings and coaches for North American math competitions, including but not limited to American math competitions such as the AMC series, AME, USAMO, and also the Canadian math competitions such as the COMC, the Waterloo exams, Euclid, so on and so forth. Today is going to be an open lecture, and we're going to be focused on the 2023 Waterloo Euclid math competition. All right, so without further ado, let's get started. Okay, before we jump to all the details, all the technical details of the Waterloo exam, I'd like to spend maybe 5 to 10 minutes talking something about the Waterloo exam. Hopefully, you guys already have very thorough understanding about the Waterloo exam and the Euclid exam especially. But in case you still have some information you want to ask, so we're going to take this opportunity to give you guys a short and quick introduction about the Euclid math competition. Okay, just want to make sure we're all on the same page. First, how does the Euclid work? So Euclid is actually a 2.5 hours exam, which contains 10 problems, and each problem worth 10 marks. Okay, so as we all know that question number 1 is way easier than question number 10. However, they share the same mark. Okay, and normally speaking, each problem will have A, B, C 3 parts or A, B 2 parts. So normally speaking, from question number 1 to question number 7, the 3 parts or 2 parts, they're basically independent. So question number A might be asking something about the function, while question number B might be a geometry problem. So if you have no idea about question number A, you can jump to question number B. Normally speaking, they're not really relevant. However, for question number 8 all the way to question number 10, these 3 parts are highly bound. So whatever conclusion you got from the A part will always be applicable in the B parts. And the same thing, it is going to be applicable for the C parts. So that being said, when you're dealing with the last 3 problems, try to pay attention. Whatever you get from question number A must be applicable to B and to C. Just try to bear in mind. It might give you a direction how to solve the problem. There are 2 types of question for the Euclid. One is basically you just give a short answer. I just need an answer. That's it. Nothing than the answer. Well, the other part is you have to show your work. Okay, this is quite understandable. Well, here's the deal. Even though some problem, they only ask you for answer, but I highly recommend you to put some work, in the exam paper. Just in case this is a quick calculation, you made some problem in the calculation process, of course your answer could be wrong. However, as a grader, as long as I see your solution process, I see, okay, your entire solution process 100% correct. You just made a tiny mistake in the final step. I can partially give you some scores. So bear in mind, even though some problem, they only need an answer, I strongly recommend you guys to put some work. That's going to really show the thinking process for the grader. Okay? And of course, for most of the problems, you need to show your work. If you just give me an answer, it worth nothing. I need to show the entire solution process, and the grader will understand where you come from. This is basically how the Euclid exam works. Okay. Second part, do I have to participate Euclid? Well, here's the thing. If you want to go for the Waterloo University, especially some very hot majors, mathematics, computer science, so on and so forth, engineering, as long as you finish your application, a few days later, you're going to be receiving an email. Well, the email is actually writing very polite. They're going to say, they suggest you, of course, there's no compulsory, suggest you to participate the upcoming Euclid competition. Well, here's the deal. There's almost like no exception. Every student who get enrolled into this very top tier, very hot majors, none of them, they ignore that email. They indeed go to the Euclid contest and then did a good job. So that being said, if you have a good score from Euclid, it's going to be beneficial, extremely beneficial if you want to get an offer to the Waterloo University. So bear in mind, this is actually something very important. And also we're talking about something about a scholarship. So on the Waterloo website, you'll see something like this. In order to be eligible for the Faculty of Mathematics entrance scholarship, so the applicants needs to take at least CSMC or Euclid. But actually, in the real practice, is like Euclid actually have way more weight compared with the CSMC. So therefore, having a good score from Euclid is going to help you to having, from 1,000 to 10,000 entrance scholarship. This is actually something very important. If you want to have some scholarship, Euclid is going to be very important. Okay. Is there any certificate for Euclid? Yes. Pretty much the same thing as most of the North American math competitions. Euclid actually provides the certificate. As long as you can basically in the top 25%, we call it a cutoff score, you'll be able to receive a certificate saying that, okay, you did a good job, and this is your certificate of your distinction. And this is kind of considered to be an entry criteria. You need to show this to your universities that you did a good job in the Euclid exam. And on top of that, if you can score even higher from 5% to 2.5%, this is going to be even more beneficial. It's going to show you that you have a strong background in the math, in the thinking process. It's going to be very helpful for Euclid and also the corresponding major applications. Okay, so there is a certificate. It is important for you to go for the high scores. Number 4 question is, are the problems in Euclid easy, fair, or difficult, right? So we have to have a rough estimation. What is the complexity score? What is the level of the Euclid math competition? Well, like I said, there are 10 problems, and each problem marks 10, right? 10 scores. And here's the deal. For all those 10 problems, they're not always the same complexity. For the number 1 to number 4 problems, there are like the simple, easy peasy problem. I'll say easy peasy, lemon squeezy. You have to do them. You have to do them right. If you lose any scores in the first 4 problems, you're actually losing something for nothing. Okay, so make sure you take out all the problems, so the first 4. And then from question number 5 to question number 7, I would say they're kind of like the mid-level complexity. They are the critical problems. As long as you have any kind of math competition trainings, not necessarily Euclid, you go to the AMC, you go to different kinds of math competitions. As long as you have some general trainings, these problems will be kind of easy for you guys. You won't be feel a lot of problems dealing with all these problems. So therefore, I give a name for these problems. These are critical problems. If you want to make your AMC, if you want to make your Euclid math competition score as high as possible, you have to minimize the problem, minimize the mistakes you did for this 3 problems. Okay, try to minimize errors as much as possible. Try to also do them right. So this is kind of like we'll say separate the cream from the double cream. You want to make sure these critical problems are always properly handled. And then question number 8 to question number 10, they are considered to be the difficult problem for sure. And this is actually the challenging problem, and try to really, really separate the cream from the double cream. And this is actually our course is going to be focused on. Our course is going to focus on the difficult problem and teach you guys the thinking process and some conditional react and different patterns, how to do the difficult problems. Okay. So as a common question, most of the students and parents, they keep asking, what kind of score is considered to be a good score for the Euclid, right? How many score I need to get out of 100? So the short answer is, if we do a statistic for the last 20 years, and then we do some calculation, we'll find out 83 will be a very nice score. 83 will guarantee you to go to the top 2.5%. This is considered to be a very good percentage, okay? As long as you get this kind of like accomplishment, that'll be good enough. Okay, how you can get 83 scores, right? We're gonna have a strategy how to make it happen. So here's like a strategy how to get your 83 scores. First thing first, your first 4 problem, like I said, they are easy peasy problem. You have to do them. You have to do them right. There's no brainer. You have to do it. That's going to give you 40 scores. Okay. From question number 5 to question number 7, like I said, they are considered to be the mid-level complexity, and you have to minimize the unnecessary errors in these problems. Making a good score in these 3 problems is going to be brutal for the entire math competition. So try to minimize the unnecessary errors, and hopefully you can get 28 out of 30 in this part. This is doable, quite understandable. And then as long as we go to question number 8 to question number 10, we kind of having some strategy. Sometimes you have to let it go. You can't really spend all your time doing this very challenging problems. So this is my suggestion. For question number 8 to question number 9, they're kind of difficult for sure, but they are considered to be the easy part of the last 3 problems. So for question number 8, you have to do it right. I think this is no problem for our trainings, for our lectures. Our students always say question number 8, question number 9, A part, no problem. Well, B part, you might not be able to do them all, but try to do as much as you could. So like I said, part of B part. So that being said, in these 2 problems, you have 20 in total. A part, for sure, you're going to do it. You get 50% of the scores, and also part of the B part. So I'm going to be a little bit, like a little bit conservative. Maybe you can get roughly 13 out of 20. You might be able to get even more, but let's say 13 out of 20. And then for the last question number 10, this is a killer problem. This is sometimes very challenging, so don't waste your time too much. Okay? You can actually save the time for all the previous problems and make sure you don't make any stupid mistakes. So question number 10, I'll just ask you to focus on the A part. If you can do the A part, roughly you can get at least 2 out of 10 scores. Okay, this is a very understandable, very reasonable strategy for you to take all your time and all your arrangement for the Euclid exam. If we add everything together, that's going to be 40 plus 28 plus 13 plus 2. That's going to guarantee you to get 83. So that being said, you really got to have some strategies. Don't take your time equally the same from question number 1 to question number 10. You have to strategically arrange your time and to make sure you can focus the most important problem, dedicate more times for those problems. And this is actually where we come from. All right. And then question number 5, this is also a question keep asking by different students. Is there any similarities between the AMC 10 or 12 and also Euclid? Because sometimes students want to do the preparations for both. They keep asking, if I just want to go for the AMC, do I still need to try some Euclid or vice versa? Well, the answer is hell yes. There are a lot of similarities between these 2 exams, and sometimes they just copy from each other. You know what? I'll give an example, and the example will speak for everything. So this is a problem from 2014 AMC 12B, question number 21. It's considered to be the last 5 problems. And if you see the year 2018, Euclid question number 8, B part, these 2 problems are exactly the same. The only difference is that Euclid actually break the original 1 problem, like this 1 figure, into 2 graphs. Okay, talking about the solution process, all the technologies, everything. If you check the solution manual, they're exactly the same. So you see, this problem, Euclid copy from AMC. Another example is, if you check the year 2006, AMC 10A, question number 8, question number 16, and 2015, Euclid number 8, B part. You see, these 2 graphs, they're even exactly the same, right? I don't even have to say too much. So that being said, these 2 math competitions, Euclid and also the AMC 10 and 12, they have huge similarities in between. So therefore, if you want to do some preparation for 1 exam, you can always use the other exam as some sample problems and help you guys to do some preparations. Okay, so that being said, these 2 exams are very similar to each other. You can use one to prepare the other. All right, so that being said, we actually give you guys a very short and brief introduction about the Euclid exam, just in case some students are not 100% familiar about the Euclid exam. So moving forward, here's like the syllabus, how our lecture is going to be organized. This is like the bootcamp lectures. We have 10 lectures in total. Today is our lecture number 1. So in our lecture number 1, we're going to talk something about the geometry session. We're going to talk something about the triangle, quadrilateral, polygon. If you check all the Euclid math competition, the statistics, that's going to give you roughly 25% of all the problems that are actually focused on today's lecture. Okay? And then in the next week lecture, we're going to be talking about the second part of the geometry. We're going to talk something about the circle and 3D geometry. Well, here's one thing I like to bring it up. 3D geometry, this is somewhat important from AMC's perspective, because every year they have some considerable amount of exam, like problems talking about this part. However, for our Euclid, this is not something so important. In the last 20 years, there's only 1 year, in the year 2017, the Euclid tested once. Only 1 year in the last 20 years. So that being said, we think like Euclid does not really put a lot of emphasis for the 3D geometry. So therefore, in our second lecture, we're going to focus more on the circle, or just take some little efforts for this 3D geometry. Of course, for this one-time problem in 20 years ever, we're going to talk about it. Okay, but generally speaking, that's going to be focused on the circle. That part actually takes roughly 8% of all the Euclid exams. In the third lecture, we're going to talk about the coordinate geometry, which is actually using the algebra way to solve the geometry problem. We can use a lot of algebra functions, solutions, try to solve some relatively complicated geometry problem. So that part, actually, if you check the statistics, it takes roughly 15% of all the Euclid math computation problems. You know, all the way comes to here, if you do a quick calculation, let's check it out. In the first 3 categories, you know, we're all talking about the geometry, right? We already take more than 40% of the coverage. Does it make sense? Yes, because Euclid actually put a huge emphasis for the geometry section. You know, Euclid is actually the name of a geometrist, right? So that being said, if you know if you have a good understanding for the geometry, that's going to be very beneficial for your entire Euclid math competition. Okay. And then from lecture number 4 to lecture number 7, we're going to be covering the algebra part. Like I said, algebra is actually scattered all over the places. Everyone learned algebra from your elementary school, right? So there's so many concepts, so many different things you need to remember. Lecture number 4, we're going to be talking about the exponents and the logarithm function. Trust me, this is very important because 1 year, they're going to test you at least 1 problem. At least 1 problem per year. They might even test you 2 problems, 3 problems, but at least 1 problem per year. Test you the exponents and algorithm. In total, it takes roughly 10% of the entire score. Lecture number 5, we're going to talk about the functions, advanced functions, polynomial. That one is going to take roughly 15%. And lecture number 6, we're going to talk about the trigonometry. Trigonometry is always a very important part, right? There's a lot of like complicated skills, a lot of like fancy, tricky ways to try to solve the problems. So by the time that we're going to teach you guys some common strategies, some common patterns, how to use the trigonometry, solve different kinds of problems. That part roughly take 9% for all the Euclid problems. And then lecture number 7, we're going to talk about a sequence and series. That will be roughly 10%. Okay. So lecture number 4 and number 7, we're going to be talking about all the algebra part. Lecture number 8, we're going to talk about the combinatorics, countings and probabilities. That is actually something important, right? Some students, they really have a hard time, you know, for figuring out the counting and probability problems. We're going to show you guys some common practice. So that's going to take you roughly 12%. And lecture number 9, we're going to talk about the number theory. Again, number theory is kind of like a very unfamiliar concept for most of the students, right? You might know something here and there, but you never get a chance to really sit down together, have a very comprehensive, well-organized kind of a summary for all the number theory concepts. So that part every year in Euclid is going to take roughly 8%. And then for our lecture number 10, we're going to take it as a question number 10 bootcamp. So in our entire lectures, we're going to focus on from question number 8 to question number 10 for sure. And in our last lecture, we're going to give you some complicated, challenging question number 10 problems, really give you guys a big direction. What are you going to do? As long as you see some complicated, scary problems, and you don't even know how to get started. How you can rob some scores, if I could use the word rob some scores, right? Grab some scores, even though you have no idea how to do the problems. There are some common patterns of thinking process, and even some kind of like format. You can please the grader and give you some scores. Okay, some student might be saying, hey, Alex, if you add everything together, why the number is actually greater than 100, right? See, if you do quick calculation, you add everything together, it's actually more than 100. And the reason behind that is that sometimes one problem is going to test you different concepts. This might be, let's say, a circle problem, right? But in the circle, I'm still going to test you some quadrilateral or triangle, so on and so forth. This might be a counting problem, but I use some sequence and series. So that being said, we're going to actually add all the numbers together. It's going to be a little bit more than 100%. Okay. And then before we jump to our lecture number 1, I'd like to say how our lectures are actually organized. So our lecture is not actually basically helping guys do all the problems. You know, there's millions of problems, right? You can't do them all, right? So the most important thing for our problem, for our lecture, which separate us from the other lectures, is our lecture always can be classified into 2 major categories. Our first category is always concepts. Fish and fishing, right? Before you do anything, you're going to know the entire concepts. We're going to spend, you know, like roughly half an hour or something, give you guys an overall introduction. What are the most important concepts that you need to know in order to basically do the Euclid math competition in this specific part? Let's say 2D geometry, 3D geometry, so on and so forth. And then for the second part, we're going to give you some problems. But most important things, we're going to really give you the important category of problems. Or we can say, what are the most classical problems you're going to be seeing from this part? So this is more like, instead of giving you all the problems one after another, we like to classify them into category number 1, number 2, number 3, so on and so forth. Really bring like the most important problems you're going to be seeing in the Euclid, and give you 1 or 2 examples for each, and you'll be able to use all those examples, try to do the other problems. So this is actually what we find out the most efficient way that help you to understand the concepts, all those kind of theorems, so on and so forth, formulas, and also the problems based on those concepts. All right, so this is basically a short and brief introduction as a warm-up of all our lectures. We have any questions? Are we all good? Okay, perfect. If you want to take a screenshot, okay, no problem. Yeah, you can actually, you know what? You can actually ask me for a video link. We'll be able to provide a video link for today's open course lecture. Okay. All right, if all good, let's jump to our lecture number 1. We're going to be talking about our 2D geometry, but basically focus on triangle, quadrilateral, and different polygons. All right, if all good, let's get started. So first concept, if you want to talk about, is actually that in the triangle, there's some basic concepts. So I think the most important concept is actually the triangle's inequality, right? In a triangle, as long as you have 3 sizes, the sum of any 2 sizes is going to be greater than the third one, which is quite understandable, right? Okay, and I think, like, you know, when you were learning this part in your day school, the teacher also mentioned something like this. There are actually 2 rules. One is the sum of 2 sizes is greater than the third one. And also the difference between 2 sizes is always going to be lesser than the third one. Right? And this is quite understandable. Okay, so my question is that if I want to list out all this kind of like relationship for the 3 sizes, do I have to list out all those 6 different formulas? Or some of them are actually redundant? Do I have to list them all? Or some of them are actually redundant? Who can tell me? So this is like an open course, but I still want you guys to have some interaction. You can maybe unmute yourself, and then you can maybe type something from the, okay? Okay, so I see Jerry says some of them are redundant. Why? Which are the redundant? You can unmute or you can type, okay? Yes, I see somebody has the answer. Yes, exactly. See, this guy, A minus B lesser than C is actually A lesser than B plus C, right? This is exactly something like this. So that being said, in the future, if you want to list out all the relationships for all those kind of three sizes, you don't really have to list out all those kind of minus relationship. The sum relationship will be good enough. So everything you got from the sum will be covering pretty much everything that you need for the minus part. Okay, this is actually a very important thing. It's easy peasy. However, this is actually something very important. This is the intrinsic inequality relationship in a triangle. Well, my second question is, besides all those like three sizes, is there any other inequality relationship for a given triangle?
Yes.
Like what?
The Pythagorean theorem.
The Pythagorean theorem?
Yeah.
But Pythagorean theorem is not like an inequality relationship. It's like a, it's kind of like a C equals underscore A squared plus B squared, right? But
Yeah.
what is the intrinsic inequality relationship? Some students say all angles add up to 120, but that's not an inequality. That's still like a relationship. That's like an equation relationship. Yes, I see somebody has the answer. It's kind of like sine theta is actually from -1 +1. Cosine theta from -1 to +1, right? Because for a triangle, you have all the angles are actually between theta between 0 to 180, right? So that being said, bear in mind, in any kind of triangle, you have such a sine and cosine relationship. That's going to actually automatically generate an inequality. Is that right? So these are two very important inequalities that you need to remember. They're so easy, but trust me, in the later problems I'm going to be showing you, we're actually using these basic things to generate some flowery solutions. Okay. Second part is everyone knows that. You learned this from elementary school, Pythagorean theorem. Everyone knows that, right? But you know what? Instead of like directly giving a triangle, a right triangle, help you to calculate a Pythagorean theorem, most of the time in Euclid, and the same thing from the AMC, is that the question is going to give you the three sizes of a triangle. So I see a student got a question. I'm sorry?
I have a question. Like, if theta is between like 0 degree and 180 degree, then why is like sine theta between -1 and 1? I think
this is more like
should be between like 0 and 1.
Exactly, yeah. But this is like a more generic relationship. Yes, you're right. Because if you want to do this, this is the relationship for sine, right? This is relationship for cosine, right? And if you're talking about something like this is from here to here. Yes, you're right. You can put it here. But from -1 to +1, this is the generic relationship for sine and cosine. We're not specifying to a very tiny range. This is more like a wider range. Does it make sense?
Yeah, thank you.
No problem. So talking about this Pythagorean theorem, the most important thing is that we need to know what is the Pythagorean triple. Because most of the time, the question is going to be giving you like three sizes. And then from the three sizes, you need to really convert it back to figure out, okay, this is actually a right triangle. So I think there are some more very important Pythagorean triples that you need to remember. 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, 17. So all these problems, all these kind of like three sizes are considered to be a Pythagorean triple, right? So this kind of Pythagorean triple is really going to help you to identify, oh, this is actually what? This is actually a right triangle, right? Okay, so if you have some questions, maybe you can put it into the group chat, because we have like 100 students. If we keep answering all the questions, that's going to take forever, right? So for our registered students, later I'm going to show you guys another session. You can ask all your students, and for all the other students, you can post those answers into group chat. I'm going to be able to give you an answer. Sounds good? Yeah. Otherwise, this is going to take forever. Okay. The next part, the most important thing we're going to talk about is actually congruent triangles. This is actually something very important. So if you want to determine two triangles that are congruent, there are some determination rules. right? For instance, you can use the 3 sizes, right? If 3 sizes are the same for 2 triangles, of course, these 2 triangles are congruent to each other, right? And side angle side means 2 sizes and their included angles are the same. So therefore, these 2 triangles are congruent to each other. Same thing, angle, side, angle. 2 angles and their included side are corresponding to each other. So of course, these 2 triangles are congruent to each other. And angle, angle, side, right? 2 angles and one of the opposite side of this angle, they're corresponding to each other. So these 2 triangles are actually congruent to each other. And especially for this right triangle, you can only have this one short leg and a hypotenuse. You can make sure these 2 triangles are actually congruent to each other. Does it make sense? I think this is something quite understandable, right? And last but not least, many students really want to put attention for this part is 2 triangles. If you have the SSA, 2 sizes and the opposite angle of one side, can you determine these 2 triangles are congruent to each other? Well, the answer is no. You can't do this because, let's check it out. I have these 2 triangles. They're blue lines, blue sizes, they're exactly the same. Okay, no problem. And they're sharing the same angle, which is 30 degrees, no problem. Well, according to SSA, so it is going to be 2 sizes and also the opposite angle of one side, right? So that being said, this guy is red. I'm going to find another triangle and make sure these 2 triangles, they have the red size. However, when you're doing this, you can find out there are actually 2 triangles for this. One is here, and the other way is here. Is it right? So that being said, you can have 2 triangles. They're basically talking about the same thing. Is it right?
Yep.
So these 2 triangles, they're kind of both SSA, right? However, you can see, look, one triangle is for sure identical from my previous one. Big red one. However, the smaller one is the black one, right? This is for sure not the same as the big one. Okay? So I see a student got a question. Will you post the notes for this class? Yes, we're going to post this note to our Google Classroom. Any student who registers for our class will be able to receive the notes. Okay. The other question, any interactions? Yes, of course, you can always ask your questions, but in a more reasonable way, right? You can post those answers because today we have 100 students. Normally in our regular lectures, we only have like 20 students. Everyone can talk. So for now, you can raise your hands and I will be able to basically answer your questions. Okay. Okay, so let's continue. So for the similar triangles, this is also a very important concept, right? For the similar triangle, so try to make sure 2 triangles that are similar, you have the following strategies. You can check the angle. As long as 2 triangles, they have 2 angles correspondingly the same. So therefore, these 2 triangles are similar to each other. Right? Because similar is actually a more loose condition compared with the congruency, right? Congruency needs to be 2 triangles exactly the same. Well, similarity, just trying to make sure these 2 triangles, they're proportional to each other. So they do not really have too much like strong condition. Well, the second one is actually SAS. 2 sizes, they're proportional to each other, and also the included angles are the same, right? And then the last one is SSS. 3 sizes. If 3 sizes are proportional to each other, and then you'll be able to see these 3 triangles, they're actually similar to each other. This is quite understandable, right? Okay, so therefore, if we do a quick comparison between the congruency and similarity, you can find out for 2 triangles, they are congruent to each other. At least you need to have a side information, right? At least you need to have a side information. If you only have angle information, you won't be able to say these 2 triangles, they are congruent to each other. However, if you're looking at the similarities, I don't really need your side information, right? Only the angle information is good enough. If you want to give me a side, okay, I'm more than happy to have it. However, there's not really compulsory to have two triangles. They have exactly the side information in order to generate. They are congruent to each other. I mean, they're similar to each other, right? This is something quite understandable. Okay, like I see students keep asking questions. Calculator, yes, you can use calculator for Euclid, but you can't use calculator for AMC. All right. So next question, we're going to use the radian or using the degree. You know what? They're all right. You can use whatever you like. It doesn't matter. As long as you do the correct conversion from radian to regular degrees, you're good to go. All right. Okay, so let's continue. So moving forward, another very important concept that you need to know is actually the sine law and also the cosine law. So what is the sine law? Let's say I have a triangle, right? The triangle have the three sizes, have the three angles. So the sine law says A over sine A equals to B over sine B equals to C over sine C equals 2R. So who can tell me what does 2R mean? Who can tell me? What does this 2R mean? You can unmute yourself and you can ask.
1.
1? No, this is 1 will be like a real value, right? But this is not like a real value. This value is going to change. I'm going to ask for Wayne. What is that?
External, like is external inscribed circle radius.
Is that right? That's actually the radius of the circumcircle, right? That's going to be the R, the radius of the circumcircle. Bear in mind, this is very important. Sometimes it's going to really help you to do a lot of calculations. Okay. Well, the other part is actually way more important than sine law, trust me, which is the cosine law. Cosine law, we actually give you guys this, right? This is like the cosine law. Cosine law actually give you the relationship about the three sizes and also the angles. So if I convert it, let's say if I converted one of things into something like this, cosine C, for instance, will be equals to A squared plus B squared minus C squared to AB, right? Well, here, let's have a quick observation. So this is an equation, right? On the left-hand side, this is only an angle, right? It's a cosine value of an angle. While on the right-hand side, these are sides. Okay? So that being said, this kind of law actually make a bridge between the angle and also the side, right? So that being said, as long as the problem give you a bunch of angles and ask you the side, or give you a bunch of sides and ask you to do the angle, always use the cosine law as your top, kind of like top choice. Because the cosine law is a very good relationship between the angle and the side. You see, for the sine law, the angle and side are actually blended together, right? A sine A, one side, one angle. However, for the cosine law, they can really segregate angle at one side while side on the other side. And this is actually very important. Really going to help you to find out the relationship between the side and angle. And also, trust me, cosine law is a very popular rule. You're going to use this theory to try to solve a lot of complicated problems. And then number 6, I think one of the very important things that AMC and Euclid, they both like to test you, is how to calculate the area of a triangle. Okay, how to calculate the area of a triangle. Well, there are a couple of ways to determine the area of a triangle. First thing first, using the definition, right? This is basically what you learn from your elementary school. That you have a top, you have a bottom, you're doing 1/2, top times bottom, good to go. Second one is the famous Heron's formula, right? As long as you have a triangle and the three sizes of the triangle has been given, then you will be able to use such a rule. A equals to underscore S times S minus A, S minus B, S minus C, where S is actually the semi-parameter, right? So you can use actually such a rule, try to determine the area of a given triangle. Well, here, I want to ask you a very interesting question. Let's say, if I want to give you a triangle, so the triangle have the three sizes, how you want to determine the area? Some students say, hey, Alex, you just told me this is the Heron's formula, right? Of course. if I give you a formula, let's say 3, 4, 5, for instance, 3, 4, 5, this is going to be a right triangle. But anyway, if I give you 3 sizes, and you'll be able to determine the triangle's area. No problem using Heron's rule. However, if I give you something a little bit nasty, under root 3, under root 5, under root 7, are you going to using the Heron's formula one more time? Or there might be some challenge. Look, if you want to use the Heron's formula, no one is going to be in your way. But trust me, if you want to use the Heron's formula, your S will be something quite nasty. This is going to be your S, right? And then your area is going to be what? This nasty S times S minus under root 3, under root 7, under root 5. Right? That's going to be a nightmare. There'll be so many under roots for you to do the calculation, and you can never make them out, right? So that being said, means as long as you are giving 3 sizes of a triangle and you are asked to determine the area of a triangle, if the 3 sizes are something very easy, whole numbers, integers, you're good to go. However, if you're looking at some nasty numbers, using the Heron's formula is going to be a nightmare. In such a circumstance, you're going to use something what we call a double. I'm going to use this thinner. A double Pythagorean theorem. What is a double Pythagorean theorem? Let me try to something like this. If I have a triangle, this is root 3, root 5, root 7, right? I wanted to determine the area of this triangle. What I can do is that, let me try to do a height here. Let's say this is going to be my h, okay? As long as I get our h, for instance, you will be able to see this is going to be my x. This is going to be my root 7 minus x, right? This is quite understandable. Well, that being said, you can actually using the Pythagorean rule on the left-hand side and the right-hand side of this triangle. Let's say if I go to the left-hand side, if I go to the right-hand side, I can always do something like this. Under root 3 square minus x squared, they equals to h squared, right? And also on the right-hand side, under root 5 squared minus under root 7 minus x squared equals to h squared as well. So that being said, you can have an equation under root 3 perfect square minus x perfect square equals to under root 5 perfect square minus under root 7 minus x perfect square. You see, this is actually a fairly easy equation, right? You can easily solve this equation. You're not going to be looking at something so nasty like this. Using such an equation, you can find the value of x, right? As long as you find the value of x, you can put it into any one of this formula here, and you will be able to determine h, right? Now you have h, and you have under root 7, you'll be able to determine the area of such a triangle. So that being said, you see, in such a way, even though you're going to basically solve the problem in 2 different steps, but you're really getting rid of this nasty, nasty calculation. Does it make sense to you guys? So try to make sure in the future, as long as you see some nasty numbers, using the double Pythagorean theorem, that's going to help you to expedite your calculation process, rather than always using the hardcore calculation from the Heron's formula. Does it make sense? All right, let's continue. The next one is going to be our shoelace theorem. So how to determine the area as long as, for a triangle, as long as the 3 sizes is not given, however, the coordinates of the 3 vertices is given. Well, a very kind of like a hardcore way is you can actually, using the distance between 2 points, right? Try to determine what's the value for the one side, and then what's the value for the second side, the value for the third side, and doing the Heron's formula as we did from here, right? However, there's a way more straightforward solution. Rather than doing something so complicated, we call it, this is the famous shoelace theorem, right? you can directly determine the area of a triangle as long as the three vertices is like the coordinates of the three vertices is already given. So this is actually something very important, especially in the coordinate geometry part, right? Instead of doing a hardcore Heron's formula calculation, we're really going to use this to do a shortcut. This is a fast track, and you'll be able to determine the area fairly quick. Try to remember this, okay? And also, this can be more generic. Rather than just doing the solutions for a triangle, you can actually find the area of any kind of polygons using such a more generic solution. As long as I give you a what we call a convex polygon. Okay, so what is a convex polygon? Convex polygon is something like this. As long as you take any kind of side, you make an extension for any kind of sides, the entire shape of this polygon is on the same side of your extension line. So that will be considered as a convex polygon, right? In our regular lectures, we have already give you the detailed explanation about the convex and the convex, right? So the convex polygon is actually the very important application scenario to use the generic form of your shoelace theorem, right? As long as you got all the coordinates of different vertices, you can plug them in and you can determine the area of such a convex polygon right away. Okay? Okay, and this is pretty much the most important thing you want to do in order to determine the area of a given triangle, right? From the basic definition to Heron's formula and all the way to using the shoelace. So trust me, these are so important, and this will be tested every single time in the Euclid math competition. All right, moving forward, we're going to talk something a little bit height, kind of like a little bit elevated. We call it what is called the Stewart theorem. So Stewart theorem is considered to be an intrinsic theorem for any kind of triangles. This does not only have to be a obtuse triangle or a right triangle. No, it can be any kind of triangles. Let's say I have a triangle. So this triangle, I have like 1, 2, 3, 4, 5, right? There are 5 different segments. I have a triangle. I find a dynamic point in the bottom, D. I make a connection. So there are 1, 2, 3, 4, 5 different segments. Okay, so there is actually an internal relationship between these 5 segments. So M times A is here, aka A equals to M plus N. E and then times N plus D times A times D equals to B times M times B, and then C times N times C. Look at that. So there's nothing really specific for this triangle, right? It can be whatever kind of triangle. However, there's an intrinsic relationship between this triangle, the 5 different segments. So that being said, for these 5 different segments, as long as you have 4, you will be able to determine the last one, right? So there's no need, you need to get all of them. As long as you have 4, you'll be able to solely determine the last one. And this is actually a very important property that is given by the Stewart theorem. Okay? So this is basically what we introduced for the Stewart theorem. And somebody said, hey, I really can't remember the Stewart theorem. Is there any kind of like shortcuts for us to remember the Stewart theorem? Yes, you can actually do something like this. This theorem, you can put it into a man and his dad put a bomb in the sink. A man and his dad put a bomb in the sink. This is actually a shortcut way in order to remember this Stewart theorem. You can just try to keep reciting a man and his dad put his bomb in the sink. That's going to help you to remember a man and a dad put his bomb in the sink. Don't say that when you cross the border, but you know what? Like generally speaking, you can always try to remember it. So therefore, this is going to really help you to basically kind of remember the Stewart theorem. Stewart theorem sometimes is going to be very helpful to expedite your calculation process significantly. Okay. And then the last two theorems, they're not super important from Euclid perspective. They're way more important for AMC. But for the sake of being complete, I like to basically give you guys this theorem. So therefore, you can just put them together as a summary purpose. So the first one is the famous Menelaus. Menelaus theorem actually means what? As long as you have a triangle, ABC, okay? And then there's a transverse line pass for this triangle. As long as you have this, then you will be able to have such a relationship. PB over PC times QC over QA and times AR over RB. You basically traverse the three sizes of this triangle, multiply them together. This is going to be equals to 1. This is very important. A lot of complicated AMY problems you can solve, by using the Menelaus theorem right away. And the second one, something similar, what we call is like a Sivar theorem. You have a triangle, and there's a dynamic point X in the middle of the triangle. And then you basically do a connection, extend it all the way to get an intersection with the other side. And then you're going to basically break this triangle into different pieces, right? And then automatically, you're going to have BD over DC, CE over EA, AF over FB. You multiply the three fractions together, that's going to give you 1. So these two theorems are actually very similar to each other, and that's really going to help you to, do a lot of flowery problems, especially in some high-level math competition. Having such a solution from these two theorems is going to be always very helpful and help you guys to do all the complicated problems. All right, so this is basically what I want to say for our lecture number 1, talking about the concepts, right? They're kind of very easy. You learn them both. I mean, you learn them all in all your regular, like all your regular different kind of like classes or courses. Well, before we jump to our questions, let's do a quick summary. What are the classical problems that you will be seeing in the Euclid, talking about the triangle, the quadrilateral, the polygon part? So generally speaking, there are 3 major categories. Okay, Euclid love to test you in these 3 major categories. The first category is actually using the cosine law. There are a lot of problems. If you use the cosine law, that's really going to help you to expedite the calculation process. So have a good understanding for the cosine law, especially when you see some angles, and then the question asks you to do some size or vice versa, cosine law is going to be your top choice. The second category of problems is always using some area-related problems, always using some conversion and compensation. Using the conversion and compensation method in order to solve some area-related problem. So this problem might not be very easy. Sometimes when you see the original problems can be very drowsy, very complicated. But bear in mind, as long as you can do some conversion and compensation from different parts of the shape, you would be able to ace out all those problems. No problem. I'm going to give you some examples. After those examples, you will understand where I come from. And the third part is there are a lot of similarities in the Euclid exam. And most of the time, similarity is not really ask you to do some side relationship, proportional, so on and so forth. On the contrary, similarity is always going to help you to do something like this. 2 shapes, their area ratio is actually equals to the similarities ratios for a fixed square, right? If I have 2 shapes, they're similar to each other, then I can say the area ratio between these 2 shapes is actually the perfect square of the similarities ratio. This is a very important conclusion. And trust me, Euclid and even AMC, they will test it from time to time. This is extremely important. So generally speaking, talking about the triangle, the quadrilateral, polygon, so on and so forth, in this section, these are the 3 major problems that Euclid love to test you. Okay, and later I'm going to be able to give you some sample problems from Euclid and show you guys how you can do problems under these 3 categories. And one more thing before we jump to the problems is Euclid actually really put a lot of emphasis on writing, right? Sometimes if you check the Euclid official solution, it's too lengthy. Not to say you basically figure out all the solutions within 2.5 hours. You just copy the solutions within 2.5 hours. You do not really have time. So that being said, sometimes you need to a little bit brief. Don't be too complicated. So in our entire lecture, I like to show you guys the writing process. How you can write something easy, brief, yet have all those details, information that you can have all the scores. All right. So that's basically what we're going to say for the concept part. Now let's go to the second part. Let's try to see some real problems, how to solve the real problems from these 3 categories. Before we move forward, are we all good? Anything all good? Any questions? So far, so good? You can always unmute yourself and then ask your questions. There's a lot of interactions. Don't be afraid. And you'll be able to ask your questions and I can answer you. Or alternatively, if you like, you can post your answers into the group chat. I'm going to be able to see watch your answers and then watch your questions, and then I'm going to be able to answer it. Okay, perfect. If all good, let's go to our questions. So like I said, we go for 3 different categories. Let's go to our category number 1, cosine law, right? How to use the cosine law to solve the Euclid problem. Let's go to our question number 1. Okay, our first problem is actually a warm-up problem. And it's fairly easy, and this is actually a latest problem. It comes from 2002. 2022, which is our last year. Okay, 2022 Euclid. Question number 7, B part. Normally, our lectures will focus on the last 3 problems, but as a warm-up, right, it doesn't matter. Let's go for a relatively easy problem, question number 7, before we can go to the relatively difficult problems. So this problem says what? Says in the diagram, triangle ABCD has C on the BD side. Also, BC equals to 2. Okay, I'm going to put all those information here. Learn from me how to put all the informations into the graph, so you'll be able to see everything. CD equals to 1. AC over AD equals to 3 over 4. Okay, AC is here. AD is here. Okay, the ratio between these 2 sizes is actually 3 over 4. And also the question gives you the cosine value of triangle ACD, which is minus 3 over 5. With all those information, the question asks you to determine the value of AB. How can you do with such a problem? This is a fairly easy problem, right? But I want to use this problem to show a lot of conditional react. You know what? In our entire lecture, we're going to keep using the word CR, conditional react. So you know what? If all the problem, you really have to think from the very beginning, oh my God, you're doomed, because you really have no time to finish all the problem, right? And the reality, like the best practice is, as long as you see some problems, you can automatically think of some conditional react. As long as I see such a condition, I'm going to do this. As long as I see another condition, I'm going to do this. So this is really going to help you to expedite your calculation process. So let's get started. I like to show you guys the thinking process. First thing first, as long as you see a fractional relationship, right? 3 over 4, this is not so easy to do the calculation, right? You don't really want to deal with all the fractions. So our first conditional react for our lecture number for this hour, this is going to be our lecture number 1's first conditional react. As long as you see fractions, try to let AC equals to 3t, AD equals to 4t. This is going to be easier for you to do the calculation because though, huh? Okay, I thought the student asked me a question. Okay, no problem. So as long as you see such a fraction number, right, your first reaction is put it into this whole number, right? 3t, 4t, these are whole numbers. It's actually a lot more easier for you to do the calculation. 3t, 4t. Okay. Now, what should I do? What should I do? So student asked me, what is t? T is a constant. T is a parameter greater than 0. This is a new variable you want to do, right? So what's next? I'll be asking for maybe, okay, many students have the correct answer. Okay, I'm going to ask maybe Luis. So what are you going to do for the next step?
Oh, I would use the cosine law and then solve for t.
Is that right? That's a brilliant observation. Why? Because let's check it out here. You want to see this little triangle, right? This obtuse triangle. This triangle, you already have the side. You already have the angle, right? This is the cosine. Cosine thing is already given. Like I said, as long as you see side and angle together, cosine law is the best way for you to build up the relationship between the side and angle. So our condition reactor number 2, as long as you see side plus angle, most likely you're going to use the cosine law. Easy peasy, right? So in triangle ACD, use cosine law. You have AD square equals to AC square plus CD square minus 2AC CD cosine ACD. Right? Now you can plug in the value. 4t perfect square. I'm actually showing you guys how to do the writing, okay? 1 square, 2, 3t, 1 minus 3 over 5. This is going to be a quadratic equation, right? Do a quick simplification. 35t squared, 18t minus 5 equals to 0. So t1 will be equals to 5 over 7, and t2 will be equals to minus 1 over 5. Of course, the minus 1 is going to be dropped, right? This is quite understandable. So now you got a value for t. As long as you got a value for t, let's check it out. You will be able to find out the value for AC and your AD. Does it make sense? Okay, I'm just going to write it one more time here. A, B, C, D, right? Now you have this is 2, this is 1, this is 3t, 7, 15. This is 4t, 7, 20. And the question asks you to determine the value for AB. Who can tell me what should I do? I'll be asking for Wayne.
You can use cosine law again because the cosine of ACD is negative, so the cosine of ACB is positive, like the exact same value.
Exactly, right? You see, the question, so basically exactly the same thing. The question give you this, you know, like the black part, right? You do the cosine law. Now, you can actually do the cosine law one more time on the blue part. This is exactly the same thing, right? So the only thing is you need to remember cosine BCA is going to be negative cosine ACD, right? ACD. And then it's going to be 3 over 5. So in triangle ABC, use cosine law again. You can directly find out the value of AB, which is 13 over 7. QED. That's it. You see, you don't have to write a lot. If you check the official solution, they give you a full page. It's too much, right? You don't really have to do that much. So far, so good. This is a very direct application using the cosine law. However, we can have something even faster. This is like the official solution. Everyone knows that. But I think we can have something even faster. I'm going to be asking for maybe Hansen. Is there anything I can do a little bit faster rather than using the cosine law?
I was thinking like using Stewart's theorem, as we can just like plug in a number. I don't know if that's like faster or not.
Exactly. Solution number 2, we can actually using Stewart. Still remember Stewart? In Stewart, we mentioned in a triangle, 1, 2, 3, 4, 5. There's 5 relation, there's 5 sizes. As long as you know 4, you'll be able to determine the last one. In this problem, they give you everything. You can directly determine the value of AB. Is that right? This is quite understandable, right? So using Stewart, there's only one equation, and you are good to go. So it totally is up to you. You can use Stewart or you can use cosine law. So these two things are exactly identical. Okay, so that's basically the solution. You see, you don't really have to write too much. You don't have to write an essay. Do something easy, you're good to go. Okay, a student got a question, why cosine BCA is negative cosine ACD, right? This part you have to know some basic knowledge for the trigonometry. This is a co-function for the trigonometry, because I'm going to give you the answer to this. We already talked about this very detailed in our lecture. Cosine pi actually equals to minus cosine theta equals to minus cosine pi minus theta. This is a core function from the trigonometry perspective. Okay, so far so good. So trust me, you see, this is like so easy problem, right? You don't have to do too much efforts and you can get it right. So easy. And you know what? This kind of little shape, a triangle has something, has a dynamic point on the bottom and then make a connection. This is quite common for Euclid. I can give you another example, but I don't want to go for that problem. Just want to show you how the problem looks like. See, our problem, this is actually another Euclid problem. This is exactly the same thing, right? This is a problem, I'll say, comes from, it's a fairly old problem from 1998, almost like 20 years ago, right? More than 20 years ago. This problem, 1998, Euclid. They're using exactly the same shape. And this is exactly the same strategy as well. So that being said, we need to do some summary, right? You can't, when you do problems, you can't just randomly do problems. You have to put them into the different categories. You see, these two problems, exactly the same shape, and exactly the same solution strategy. All right. So these are actually a very easy problem. Now let's go to a relatively difficult problem. Still, you can see using cosine law is one of the best practice. Let's go to our second problem. So this is a problem that comes from 2001, Euclid, question number 10. It's the last problem. And you can see this is using exactly the same strategy. So let's have a quick look at it. So the problem says, point P and Q, they are located inside a square ABCD, okay? Such that DP is parallel to QD. I'm going to highlight this. DP and QB, these two lines, they are parallel to each other. Here, parallel, okay? And DP is the same as QB, which is the same as PQ. So basically, you see these 3 little segments, right? They're actually the same altogether. Okay, with all those information, the question asks you the minimum possible value of triangle ADP. Okay. All the way comes to here. Again, before we jump to the calculation, let's try to do some quick analysis. When you're reading this question, there are some signal words. We need to have some conditional react. As long as the question gives you some condition, blah, 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 and let you to determine the minimum possible value or the maximum possible value. I mean, what kind of things can generate the minimum or the max? What kind of like mathematical tools can basically build up something like minimum or max? Who can tell me? Yes, I see many students have it right. I'm going to ask for maybe Ashley. Is that Ashley Zhao? So what kind of like
an inequality?
is that right? Yes. So as long as you see mix or max or minimum something, so a conditional reactant number 3 says minimum max means inequality. Right? So that means that maybe in this problem, you really have to generate or construct an inequality in order to make it work. Which makes sense, right? And then the question give you side, the question is all side, right? QB, BQ, like AP, like PD, so on and so forth. And then the question asks you to determine angle. What is our conditional react? What would I need to do? What kind of technology in order to do the side and angle relationship? Cosine law, right? Sophia has the correct answer. Cosine law, right? This is exactly what we mentioned. So you see, this is our conditional react number 3 and number 4, minimum max inequality. And this is kind of like a side angle relationship. That's going to be the cosine law. Also, before we move forward, I think there's another very important conditional react. I like to bring it up. You see this problem, the DB, the DP, PQ, QB, 3 segments, they're actually flying there, right? They're not touching each other. They're kind of like flying in the middle of like the shape, right? So of course, if they're flying there, there's no way for me to do, right? I have to kind of like making some relationship between these 3 flying segments. I think the best way is to put them into triangles, right? As long as you put them into triangles, it's very easy to use all the rules, all those kind of things, so on and so forth. So this is actually our conditional react number 5 we like to talk about in today's lecture. Whenever you see flying segments, right? They're not really touching each other. The most important thing is you're going to make them landing, right? You have to be not flying, you have to landing. And most preferably, you're going to landing them in triangles. Does it make sense? If you let them landing in triangles, maybe most of the problem can be resolved. Okay, so with all those information, what is the best practice on the most straightforward way in order to, landing them, make them into triangles? Who can tell me? A very straightforward way to make auxiliary lines based on our conditional react. I'm going to be asking maybe Jerry Lee.
You could extend DP and QB.
Right? That's a perfect observation. We can just do a quick connection. Do a connection of this and do a connection of this. All right, why I'm doing this? Let's try to see. Okay, no panic. Let's try to see if I do Y, I can just consolidate the problem and make it a lot more straightforward. Let's check it out. So now you're telling me there are 3 segments that are the same. Try to make my life easier. I'm going to let PD equals to QB equals to PQ equals to A. Okay, that's going to make my life easier. A. And as long as you do a connection between BD due to this kind of symmetric property, this is going to be the meet, right? This is going to be the meet. A over 2. This is quite understandable. The entire shape is symmetric. So when you do this we totally, do this kind of like, you can find the R, which is the midpoint of PQ. Okay, and I do the PB. It's okay. I'm going to let PB equals to B. It doesn't matter, right? You can let PB equals to B. And the question gives you a shape for this original square. We can, just for our simplicity, we can let AB equals to BC equals to 1. Okay? So you can let whatever value. You can put C if you like. It doesn't matter. But just try to put 1 to make our life a little bit easier. Now, you are trying to determine the value of ADP. Okay? ADP. ADP is here. I'm just going to give it maybe theta. Okay? You want me to determine the value for ADP? I'm just going to give a value, let's say theta. And of course, this guy is going to be 45 degrees minus theta, right? Because BD is actually the bisector of angle ADC. All right. As long as I have this, like I said, I'm going to use some cosine law in order to make sure I can do all my calculations. So rich triangle is the most straightforward triangle for me to start my cosine law. This triangle needs to have the condition given by the problem, the 3 blue lines, right? And maybe some problems that we figure out by our own, or maybe BP, so on and so forth. Yeah, I see Isabel has a question, has a solution fairly quick. You see, this may be a triangle that we like to see. Let's have a quick look at it. In this big triangle, you're kind of using the blue condition, which is PD, and you're kind of using the BP, which is the red condition you created. So that's very nice triangle for you to do all your calculation, right? So therefore, in triangle PBD, using the cosine law, you're going to have cosine 45 degrees minus theta, a squared plus 2 minus b squared 2a root 2. Okay, if you don't understand where does root 2 come from, this is root 2, right? Your diagonal is going to be root 2, given the two sizes, right? Which is 1 and 1, so the diagonal of the square is going to be root 2, which is quite understandable. All right. Now you finish your first cosine law, which works fine, right? In this big blue triangle, this big green triangle, you have such a relationship. Well, this relationship, you have 3 variables. Cosine theta, you have A, you have B. You're probably going to find another relationship for this guy, right? In order to make our life a little bit easier. Who can tell me, is there some other triangles that I can kind of, do something or redo something that I did for the cosine law and then make my life a little bit easier? Think about it. We have already used this PD, right? And BQ is okay. BQ is more like symmetric to PD, right? So I don't have to worry about it. But I didn't really get a chance to use my PQ, right? The question still gave me a PQ. I probably have to use the PQ in order to make it work. Where I can use my PQ. You see, this is all very rational thinking, right? The question gave me 3 segments. I already used 2 of them, but I have to use the other one. But how can I use the other one? I use 2, I'm going to use the other one. There is a triangle right sitting there, and then very easy for you to use. I'm going to ask maybe Wayne.
DPR.
Is that right? That's a brilliant observation. You see, in this triangle, see, this triangle is exactly what I want to use, right? It also has the blue PD, but it has the PR, right? PR is kind of like right there, right? So I never used PR in the previous one, so this one I'm going to be using PR. All right. So in triangle PDR, I'm going to redo the same thing. Cosine 45 degrees minus theta, a squared root 2 over 2 perfect square, a over 2 perfect square, 2a root 2 over 2. Which is quite understandable, right? This part, let's try to do a quick simplification. This guy go to cosine 45 degree minus theta, 3 over 4 a squared, 1 over 2, a root 2. Now I have 2 equations. Now I have 2 equations. How can I move forward? Paul.
You just combine them because they're both equal to cos 45 minus theta.
Is that right? This is an intuitive thing, right? Of course. number 1 equals to number 2. You have a squared 2 minus b 2a root 2. These are very understandable thing, right? This is not a rocket science. You'll be able to do it right away. Okay, do some quick simplification. You find out b squared equals to 2 minus a squared over 2. This is going to be my number 3. Okay, all the way comes to here. You have to understand where we come from. This problem is not asking you to determine what is A, what is B, right? You do A and B things for your own convenience. The question is asking you to determine the value of ADP, aka you're going to figure out a value for the cosine theta or cosine 45 theta. So intuitively, your goal is try to find out a value for your cosine thing, right? It's either here or here. You can't really get lost for A and B. So now you kind of find a relationship for A and B, b squared equals to 2 minus a squared over 2. Intuitively, you want to put it back, right? You want to drag this back to the original cosine expression because your original goal is trying to determine cosine, not to determine your A and B. We put 3 into 1. Cosine 45 degrees minus theta is going to be a squared plus 2 minus 2a root 2. Just do some quick calculation. There's nothing really special. And this guy is going to give you 4 root 2 as the denominator, 1 over this, 3a plus 2 over a. Okay. All the way comes to here. What are you going to do? This is like given, right? What do you want to do? At the very, very beginning, our conditional react already told us, I need to find out what? An inequality relationship. And then try to determine the maximum, the minimum, so on and so forth. Don't forget where you come from. Now, you are kind of like on your way, right? You get a cosine 45 degrees minus theta all the way comes to here. How can you generate the inequality relationship? Who can tell me? How can you do the inequality relationship? This is already given here. Yes, I see somebody has the answer. Yes, because you can directly use your famous AM, GM, right? Because A plus B is greater or equal to 2 under root AB, right? So that being said, this guy will be greater or equal to 2 under root 6. Come on, this is question number 10, right? Even though this is not a super difficult problem, it's a little bit comprehensive. They're going to use different pieces all over places, put them together to make it work. See? So easy, right? Okay, if that's the case, let's try to do some calculation. Therefore, cosine 45 degrees minus theta is greater or equal to under root 3 over 2. Because cosine is actually a decreasing function. So 45 degrees minus theta will be less or equal to 30 degrees. Theta will be greater or equal to 15 degrees. So the question asking, what is the minimum value for theta? That's the question asking, the minimum possible value of theta. So of course, theta equals to 15 degrees, QED. You see, I'm not writing the essay for this. It's just only a couple of lines, but you actually list out all the important steps in order to guarantee you to get a full mark, right? So that being said, this is extremely important that every single step, there is a rational. You need to use all those like a rational thinking process in order to make it work. Okay, so far so good. Yeah, a student got a question, why do you know that DB bisects your QR? You can actually using the like symmetric property because everything's symmetric, then you can basically see BD actually bisect this. Student got a question, what is AMGM? AMGM is very important concepts. That's the arithmetic mean and geometric mean. In our regular lecture, we have already explained a lot. So you can do some Google search, okay? So this is actually very important. We're gonna be covering it in our lecture number, lecture number 7. when we were talking about the functions, the inequalities, this will be there. So now you can just take it. All right. Are we all good? So far, so good? Any questions? Perfect. You see, this is a very rational thinking process, how to do the problems. Okay. So I think 2 problems is good enough, right? They really give you guys how to think when you're dealing with this kind of cosine law related stuff. As long as you see the size, you see the angle using the cosine law, and we actually give you 5 different conditional react in order to make it happen. Okay. If all good, let's go to our second category. Let's try to talk about something area. When you're dealing with the area, there might be some compensation and conversion method. What is that? Let's try to deal with that with a real problem. Okay, this is a problem that comes from, let's see, 2012 Euclid. Question number 9, B part. Okay. So the question says, in a diagram, you have a quadrilateral ABCD, has 2 points MN on 2 sizes, respectively, and AM over AB equals to NC over DC. Let's try to highlight it. AM over AB, NC over DC. Okay, they're kind of like in the middle of nowhere, right? These are 2 different things, right? They're really far away from it. Okay, anyway, we just put it there, okay? Nothing really special, we'll put it there. Line segments AN, DM, they intersect as P and P, while BN and CN intersect at Q. Proof that the area of quadrilateral PMQN. Let's try to prove it. PMQN is here. Ah, this is really nasty quadrilateral, right? It's actually flying there. It has nothing. I really have no idea how to determine the area, but just put it there. Equals to the sum of the area APD. APD is something here. It's also very, what should I say, shabby, kind of like little nasty triangle on the right, on the left, and BQC. BQC. Oh my God, this is going to be a nightmare. You see, my blue one is like the twisted shape in the middle, and then equals to the sum of these 2 weird triangles on the 2 sizes. I totally have no idea how to do this, right? This is totally insane. Well, this is actually the conditional react we like to teach you guys in today's lecture number 6. As long as you see some weird shape, okay? And some of them is actually also flying there, floating there, right? So on and so forth. The question asks you to determine the area. You always want to do some conversion or compensation. What does conversion or compensation mean? It means you always want to maybe add something or subtract something to make sure your weird shape could be something more reasonable, more understandable. Like I said, the blue one is totally weird in the middle, and there's 2 red ones, they're triangle, but you have no idea how to determine. They're totally, tilt triangle in the middle of nowhere. So most of the time, as long as you see these weird shapes, you always want to do some, add something, remove something, and then hopefully you can make your shape a little bit understandable. That's basically a common strategy where we come from. So that being said, in such a problem, the question is basically want to show, right? WTS means want to show. Want to show means I don't really have the solution, but this is my thinking process. The area of PMQN is the sum of the triangle APD plus the triangle BQC. But like I said, they're kind of like flying there. I can't really put them together. Is it possible I can add something, remove something? I don't think there's too much we can remove, right? Is it possible I can add something and just try to make the shape a little bit, good looking or easy manipulation? Is there anything like in this picture, in this diagram, or in this figure? It looks very kind of like if I put it in, maybe it can make our life a little bit easier. Yes, I see many students have the correct answer. Yes, you can see here, there are two green triangles. They could be added into the shape, and they could maybe make our life a little bit easier. Because, like I said, if you want to show these two sides are the same, right? So if I want to add PMQN, add triangle PDN plus triangle QNC, I can prove this to guys. QC, triangle PDN, triangle QNC, right? This is my green one. I'm just going to highlight it. This is my two green ones. This is my two green ones, right? So if I can show this equation holds, of course, that's going to be the same thing, right? I'll be able to show the original one works because I add the same thing on the two sides of this equation. This is what? My blue one plus little green one plus a big green one. This is the area of triangle MDC, right? The big triangle MDC. Does it make sense? So want to show the area of triangle MDC equals to, so let me check. This little green one, this little here, here, here. The little red one plus the big green one, this is going to be our triangle ADN, right? And this guy, this guy, this guy, the larger red one plus the small green one, this is going to generate our triangle BNC. Okay, if you can prove triangle MDC's area is the same as triangle ADN's area plus triangle BNC's area, then your work is done. Does it make sense? I would say these three triangles will be much more understandable than otherwise, right? At least these triangles are actually kind of like sharing the same bottom. At least some of the bottom are the same, and then I can try to do something. This is quite understandable, right? Okay, how to determine the triangle's area MDC? That's a big triangle. I do not have anything really special. I'm just going to say, maybe I'm just going to do a height. I'm going to do a height, okay? And let's say I'm going to give a name to the height, maybe M. So my triangle, this guy, is going to be 1/2 M times DC, right? Okay, maybe I'm going to let DC equals to X. Just try to make my life a little bit easier. M times X. 1/2 M times X. That's the triangle MDC, the big triangle's area. Then what about the small triangle AND? AND is here, right? Maybe I'm going to do exactly the same thing. I'm going to make a height. I'm going to call this as A. Okay, I'm going to call this as A. So this is going to be 1/2 A times DN. Okay, DN is actually, this part of your bottom, which makes sense, right? And last but not least is this guy, my triangle BNC. my triangle B and C, I'm going to make a height, and then that's going to be my B. So 1 over 2 B times the bottom is NC. Rich, all the way comes to here, this is understandable, right? There's nothing too flowery, nothing too complicated. Okay, so now you're actually looking at two parts. So one, you have like a DN, one you have NC, and they're both sitting on a DC line, right? So I'm gonna do maybe another quick thing, just try to make my life a little bit easier. There's nothing too flowery, too complicated. Maybe this part, I'm gonna call maybe this is TX, because DC is equal to X, right? This part I'm gonna give a TX. And this part I'm gonna call maybe 1 minus TX, right? Nothing really special, right? And you'll be able to see that right away. So that being said, you can actually simplify your calculation a little bit. So I'm gonna use this as TX. I'm gonna use this as a 1 minus TX. There's no rocket science, right? I'm just basically replace it using a little bit T minus D, try to make sure there are not so many variables flying there all over the places. So that being said, I want to show, if you do some quick simplification, M equals to TA plus 1 minus T times B. Because X, here, 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 all the X's will be canceled. Which makes a lot of sense, right? Okay. The $1 million question is, how can I prove this? M equals to TA 1 minus TA. M TA 1 minus T. 1 minus TA times B. So this is going to generate our conditional react number 7. So all these conditional react, we're actually introducing them in our regular lectures, but for our bootcamp, we're just going to highlight it, right? Put them together. What is the conditional react for this guy? Here is the important part. Now you are looking at something like a trapezoid, right? This is a trapezoid. You kind of like having a trapezoid, and then there are some kind of like, there are like some height, right? And then you have the 3 sizes, you have all the sizes of trapezoid. Trust me, as long as you see a trapezoid, this is going to be a very important conditional react. I'm going to use the color green. As long as you see a trapezoid, A, B, C, D, whatever, always, what you're going to do is you can make a perpendicular line from the top to the bottom, right? And all your magic is basically going to happen in this little triangle. Because this part is going to be your bottom minus your top, right? BC minus AD. This is going to be the height of your trapezoid. And this part you can always use in the Pythagorean theorem, and then you'll be able to figure out what's the value. So trust me, this triangle is very important, and all of these discussions will be happening in this triangle. Okay, so this is our conditional react number 7. See a trapezoid, want to make a height. Oops. See trapezoid, you want to make a height. Okay? All right. With this conditional react, let's go back to this question. How can I solve this? M equals to TA 1 minus T minus B times B. I'm going to basically drag the shape here. I'm going to drag it here one more time to make sure you can understand it. You can see it a little bit clear. This is my shape, right? And this is even something in the middle, M. Your A, your M, your B, right? And this is your E, your F, your N, right? Here, I want to make a perpendicular line. This is going to be our D. Okay. As long as you have such a shape, like I said, all the magics happens here. This is going to be your magic triangle. So in this magic triangle, I think the only thing that you can do is kind of, let me try to give you a bit. This is A, right? This is your M. This is your B. Okay. In this magic triangle, I think the most important thing you can do is, let's say this triangle actually have kind of like this. I'll give you a name. This is R, for instance. So you can use the similarities basic relationship, right? MR over MD over DB, excuse me. MR over BD will be equals to what? Will equals to, okay, let me see if this is D or S. Let me check the original graph. The original graph is here. Oh, D is here. Okay. AMAB. Okay, no problem. I'm going to give a name S. Maybe S is actually easier. S. Okay. MR over BS equals to what? AM over AB, right? This is like a given, right? MR is here, my green one. I'm going to use the color green. Over BS. BS is the bottom. Equals to what? Equals to AM over AB. For sure, right? This is quite understandable, right? It's using the basic relationship. But let's try to see AM over AB. Is it like a deja vu? Maybe I see this AM AB somewhere, right? This is not a new thing. Did I know first the AM AC? Oh, yes, here. AM over AB equals to NC over DC. Oh, so that being said means what? I can directly use a relationship. NC over DC. Right? This is understandable, right? Very understandable stuff. AM over AB equals to NC over DC. If that's the case, let's try to see if there's anything, because my goal is try to prove this, right? I need to see what I can put into such a relationship. MR, what is MR? MR is easy. MR equals to M minus A, right? MR is M, this is M, this is A, M minus A. What is BS? BS equals to the bottom minus the top, P minus A. Is that right? This is not a rocket science, right? This is exactly what is given by the problem. And this part. This part is already done. But what about NC over DC? NC, DC. This is my NC, right? And this is my DC. This is exactly 1 over T, X over X. Exactly. X could be cancelled, right? So therefore, M minus A, B minus A equals to T, 1 minus T. You know what? If you do a quick simplification, this guy is indeed equals to M T times A, 1 minus T times B. That's it. This is exactly what we want to show here. QED. See? Easy peasy. Fairly understandable, right? There's nothing complicated, and you can do the problem very quick. So far, so good. So this is actually a very understandable problem, right? You can just basically use this problem and you'll be able to solve it. If the question gives you some flying parts, right? Some kind of like a weird shape, try to do some conversion, compensation, so on and so forth, and then you will be able to solve it. Are we all on the same page? Are we all good? So far, so good? Perfect. If all good, let's go to a second problem. The second problem is going to be looks very drowsy, very complicated, but if you use the same strategy, you can solve the problem very quick. So the second problem is here. This is a crazy problem. If you check the Euclid official solution, that's going to be super, super long. It's too complicated. But using my solution, a couple of lines, you make it work. This is a problem that comes from 2013 Euclid, question number 9. Like I said, the official solution is too complicated, and try to use my solution, you can solve it in no time. Yeah, this is our first lecture. Maybe we're going to be running out of time, and we might be do like we might drag our lecture like a little bit longer. So yeah, you know what? We're already almost like 2 hours. Let's go for a 5 minutes break, and then we're going to resume after 5 minutes. Okay, let's go for a 5 minutes break. Do some bio time, and then. Yes, we have some free courses. So if you can scan this barcode, my assistant will be able to send you the free courses. We have like 100 hours free lectures, and then you'll be able to just have some idea about it. All right, I think we can continue. Okay, we can continue. If you do not really write it down, you can do a screenshot and then maybe try to add her later. All right, so let's continue. Okay, so this problem is a challenging problem, but let's try to see how we can solve this problem in a very smart way. So the problem says, let's go for our question number 8, right? Like I said, A part and B part are always some relationships. Let's go for the A part first. You have a square. So the square actually WXYZ, they have a side length equals to 6. I'm going to write it down here, 6. And it's drawn, as shown, completely inside a larger square. EFGH, the side length is 10. Okay, so that the square do not touch, and the WX is parallel to EF. So this guy, parallel. Okay, no problem. Okay, that's it. With all those information, you want to prove the sum of the area of the trapezoid EFXW. Let's try to use a color. EFXW, that's the red one, right? And the trapezoid GHZW. These two guys. Okay, the sum of the area for these two guys is the same. Okay, that's not dependent on the position of WXYZ inside EFGH. So long story short, you want to prove these two guys actually what? Has a constant sum, right? The area between these two trapezoids, adding them together is a constant. Now you know what, there's nothing too flowery. If you want to determine the area of the trapezoid, you can just basically use the formula, right? So let's say, I'm gonna say the area of EFXW, this guy, this is gonna be the top plus the bottom, and then times the height. The height, I'll say this is H1. Okay, there's nothing I can say. Is 1/2 top plus bottom times H1. And what about the second one? The second one is the one in the bottom. That's the ZYGH. That's also 1/2 top plus bottom times H2, right? The same thing, this is going to be H2. The question says the sum of these two guys is independent with the position of my internal white square. So adding them together, this is going to be the sum will be equals to 1/2 16 H1 plus H2. What is the value for H1 plus H2? Is there anything special for H1, H2? Who can tell me? This is something so easy, right? Yeah, H1, H2 actually equals to what? Like the size difference between the big one and the small one. So therefore, 16, 10 minus 6. So that's going to give you 32. See, question number 1, easy peasy, right? There's always number 1, this A part is easy. You don't have to spend too much effort. You need to do them. You need to do them right. And also with this knowledge, I think what you can see is that not only the two red ones, they're having this relationship, and these two blue ones, they're the same, right? Because they're basically identical, right? A part, easy peasy. Don't forget, as long as you do A part, our conditional react to number 7 or this is number 7, number 8. A part always be applicable for B part. Okay, I don't even know what B part is, but let's just park it there. B part. B part said a large square ABCD is shown with a second smaller PQRS, pretty much the same thing inside it. So the square doesn't touch. Line segment AB, AP, BQ, CR, DS are shown, dividing the region between the squares into 4 non-overlapping convex quadrilateral, as shown. There's nothing really special. If the sides of PQRS are not parallel, okay. Previously it was parallel, right? But now it's not parallel, okay, to the side of ABCD. So long story short, like the one in the middle, right? This little square in the middle is no longer parallel, not like the first one, right? To the big one. And now you need to prove the sum of the area of the quadrilateral APSD. APSD. BCRQ. Okay, these two weird shape quadrilateral equals to the sum of the quadrilateral ABQR. ABQP, excuse me, ABQP, and CDSR. This is difficult, right? You wanted me to prove these two blue guys, adding them together is the same as these two red ones, adding them together. Well, ce n'est pas facile, right? This is not easy because this is like tilting there, right? There's no way for me to basically find out the top, the bottom, all these kind of tribes, I think. But like I said, A part must be applicable for B part. There must be some kind of like a rational between the A and B. Otherwise, they won't give you an A here, right? Is it possible that I can reuse something from A, try to solve the problem in B? You're going to be really bold to make such an assumption because A is actually parallel everything very right. But B is totally tilted, totally have no idea what they're talking about, right? How can I make sure I can do some magic, try to use whatever I did for A, somehow use it in B as well, and then make sure I can, do the same thing for the B part. Okay, I see a volunteer. I'm going to ask for Jerry. Yes, Jerry Chen. Yeah.
Yeah, I'm having the idea, but yeah, I'm not actually like rigorously proving it. But I think I can draw like a square that is parallel to like DC and AD and AB and BC inside the square PSRQ, so that like the redrawn square has its four vertex touching the size of the smaller square.
I think that's a brilliant idea, right? So maybe I'm going to do a quick modification. Instead of inside PQRS, I'm going to make it outside to make sure that one is actually parallel to the big square. Because in that way, my first graph and my second graph is somewhat similar. So what I'm doing, if you don't know what I'm trying to say, I'm going to keep the graph like this. I'm going to do something like this. I'm going to create a square like this. As long as I make such a square, I'm going to do a connection. If I do this, I kind of like create something similar to the first problem, right? They're not 100% same, but kind of like similar to the first problem. Then I can use whatever I got from the first problem and try to solve the problem here. So my goal is try to break your blue parts, your red parts into different regions, and then try to see if I can solve it. This is the only way I can reuse whatever is given for the first problem. Does it make sense? Sometimes you need to be very bold to make such assumption. So I'm going to give you the graph. How this is more like my scratch, right? I'm going to give you a much nicer graph. Something like this. Yes, I'm going to put it here. Make a little bit smaller here. Okay. Now, okay. This is exactly what I did, right? Previously, I have this little PQRS here. Now I'm going to use this to highlight it. This is actually the square I created. Try to make it touching different pieces. And then something like this. Does it make sense? This is quite understandable, right? Okay. As long as I have such a shape, automatically I can say something like this. I think you won't be so drowsy. This guy, the little E triangle, F triangle, H triangle, G triangle, they're all congruent to each other. Does it make sense? Is this something understandable? These are all congruent to each other, right? So I can say that E equals to F equals to G equals to H. That one makes sense, right? Because you have a triangle squeezed in another triangle. This is actually something quite understandable. And I can actually put it as a conditional react, right? If you have a triangle here, and then you have another triangle. If you have a square, another square, put it in. Sorry about my harbor drawing. So automatically, these 4 triangles, they're all congruent. Does it make sense to you guys? Yes or no? This is something quite understandable, right? You should learn that in your regular courses, right? This is actually, let's say, conditional react number 8. One square insert in the other square, and then of course, all those kind of like 4 little triangles, they're basically the same. Okay, if that's the case, let's try to do something like this. From our number 1 part, A part, what do I have? I'm going to have something like this. Use here. This guy, blue one. And this guy, blue one. If I adding these 2 guys together, that one is going to give me the same value. If I use this green one, and the green one, right? Does it make sense? This is what I proved in my original part A, right? So say from A, blue plus blue equals to green plus green. AKA means what? A plus R, that's the blue one, A plus R. C plus N equals to B plus M, D plus S. Does it make sense? Yes or no? This is understandable, right? Because this is exactly what I proved in my first question. Okay. And also I know E, F, G, H, right? Let me have a look at what the question is on me to prove. The question want to show is A, B, Q, P, C, D, S, R, B, C, R, Q, A, what is the last one? A, B, Q, P. This is what the question asked me to do, right? Let's have a look at it. What does it mean? A, B, Q, P. A, B, Q, P. A, B, Q, P is more like what? A plus S plus E. Is it right? A, B, Q, P. If I highlight it using black, this guy. This guy is A plus S plus E. The same thing, CDSR is C plus G plus N. And the other one is B plus F plus R, D plus H plus N. This is not a magic. You just basically, as long as you can read the graph, you can just plug in the values. That's it, right? Well, this is what I know. I know this. I know this. But this is what I do not know. There's a gap between it, right? I need to bridge the gap. I need to bridge the gap. How can I bridge the gap? It's a little bit challenging, trust me. This is the challenging part of such a problem. Okay? Like I said, this is what I know. This is what I do not know. I want to use from what I know to calculate what I do not know. Okay. How can I make it work? You're going to use some tiny calculation for this part. Let's try to zoom it a little bit. Let's try to pay attention to this yellow triangle, R. Okay, yellow triangle, R. Also this yellow triangle, N. Let's have a quick look at it. What's the value for R plus N? R is actually a triangle. So in order to determine the area, I have to know the bottom. This is my bottom. I have to know my height, right? Height, I'm going to give a name if this is H1. So this is going to be what? 1 over 2 QX times H1. This is going to be my H2. 1 over 2 QX. So QX mean will be SC, right? SC. H2. Because I just mentioned all those 4 red triangles, they're congruent to each other. So therefore, QX is the same as SC. So 1 over 2, I can use QX, H1 plus H2. What is H1 plus H2? This is something similar. H1 is here, H2 is here. They're considered to be the difference between the 2 big squares, right? Let's say this is X. The big square has a side length X, and this is Y. The small square has a side length Y. So this is going to be 1 over 2 QX, X minus Y. Does it make sense to you guys? Are we all on the same page? Yes, this is something understandable, right? Okay. If you do something like this, you know what? You can do something for these 2 green triangles as well. Your SM plus S will be also equals to this guy. Which is understandable, right? They're all the same thing. So therefore, M plus S actually equals to R plus N. This is the only tricky part you want to understand in this, which is also understandable, right? This is not a rocket science. Okay, why I'm doing this? Because I'm going to solve the problem in one line. That's it. Because A plus R, C plus N equals to B plus M, D plus S, right? This is what you told me here, right? Now you are telling me N plus S equals to R plus N. I'm going to add N plus S minus R plus N. This is going to be 0, right? Because these 2 parts are exactly the same. Add R plus N minus M plus S. This is going to be 0 because these 2 parts are going to be the same. You know what? do some quick simplification. Here, it's going to generate A plus S plus E, C plus G plus M. Here it's going to be B plus F plus R, D plus S plus N. That's it. This is exactly what you wanted me to prove. QED. That's it. That's the solution for such a problem. Trust me, if you check the Euclid official solution, it took, I don't know, 3 pages, 4 pages, very complicated. I don't know, because I don't even know what I'm talking about. Okay, but using my solution, so easy. That's it. You don't, there's nothing too tricky, right? You just basically read the graph and you know what you're doing. That's it. So this is considered to be a very challenging problem. As long as you see some weird shape, like I said, some tilting there, always try to do some compensation, conversion, and then you will be able to wrap it up fairly quick. So far, so good? Yeah, that's actually our second category. If you still have some time, we can go to our third category. Okay, we're kind of like over our time, but normally speaking, our lectures is like 2 hours sharp. So let's go to our last category. Last category is actually using similarity. Try to solve the problem, and most likely is the areas ratio is also the similarity ratios for fixed square. So let's go for one problem. That's going to be the last problem for today's lecture. Number 3, there you go. That's the problem. Like I said, we always give you some relatively difficult problem because the easy problems, you can figure them out by yourself, right? So now we're looking at a problem that comes from, what's the date? What's the 2001 Euclid question number 9. Okay, let's have a look at it, how this problem works. So this problem says you have a, I'm just gonna drag it here. Okay, so this problem, let's have a look at it. How are we gonna deal with this problem? The problem says you have a triangle ABC, which is right angled at B, and have the side lengths, which are integers. Okay. Side lengths, which are integers. Normally speaking, for a triangle, the side length does not have to be a triangle, like an integer, right? A triangle's sizes does not have to be like an integer. You can be fraction number, you can be real numbers. But why? Something does not have to be an integer, but a question set to be an integer. This is actually our conditional react. Number 9. Or maybe number 10, right? I'm not really good at counting the numbers. As long as something does not have to be integer, but give you an integer, most likely we're going to do some number theory. And in the Euclid territory, the number theory are fairly easy. We're not talking about Fermat principle, Euler's torsions formula. That's more like for AMC and AME. This is more like for the factorization. Maybe you're going to do some factorization for this problem in order to make it work. Conditional react, I don't know if this is going to be used or not. There's no guarantee you're always going to use it. But you know what? Always good to put it there. A second triangle, PQR, is located inside ABC as shown, such that the sizes are parallel to AB, BC, AC. And the distance between these 3 sizes are actually 2. So they're parallel to each other, and you just basically make sure they're like 3, right? 1, 2, 3, 3 sizes, they're all 2. And here, please determine the side lengths of all possible triangles, like the side lengths of all possible triangles of ABC, such that the area of ABC is 9 times of the area PQR. area of ABC is 9 times of area PQR. Obviously, these two triangles are similar to each other, right? They're basically parallel all sizes. So you're trying to say that the similarity ratio is what? 3 to 1. Is that right? If two areas, if two sizes, two triangles, they're similar to each other, the area ratio is 1 to 9. So the similarity ratio is going to be 1 to 3. Does it make sense? Which is quite understandable. So that being said, you can just basically try to do some quick calculations. As long as you have the 3 sizes, they have like a 1 to 3 relationship. So you have a big triangle. Let's say this is A, this is C, this is B, right? You have the 3 things. And then automatically, this is going to be what? B over 3, C over 3, A over 3 for the little small triangle. This is something quite understandable. Now, I need to find out some relationship, right? If there's no relationship, how can I make it work? I need to have an equation in order to make it work, right? Who can tell me what is the very conspicuous equation to make my calculation, to make everything work? Big area, small area, I know, right? And is there anything I can make some quick equation just to wrap it up? Because I need an equation to do all my magics. If there's no equation, of course, I can do nothing, right? Who can tell me? I'm gonna ask for, what is this guy's name? Like this radiation sign. Okay, Jerry?
I have an idea. It's like you connect PA, QB, and RC, and then you
Okay.
have a trapezoid, and then the ratio of the top to bottom is 1 to 3, and you can do some calculations with that to find the
Okay. That's a very brilliant observation. So if I just want to do a connection, so of course I'm gonna put it into 3 different trapezoids, right? That's my green one. And what about this is my red one, my yellow one. And this is gonna be my blue one, for instance, right? As long as you break the big shape into 3 trapezoids plus a small right triangle in the middle, is there anything you can do very conspicuous? What is, you can, like the picture already tell you, there's a relationship. There's a relationship there. What is that? Try to think something easy. You have a big triangle, right triangle. You break it into 3 trapezoids plus a little red one in the middle. What can you do right away? Trapezoid? I mean, like the, okay, Pythagorean theorem. I'm gonna ask for Sophia Liu. What do you find out? Yeah, there's something very conspicuous.
Like the area of the 3 trapezoids plus the small triangle is the big triangle.
Is that right? This is more like from elementary school. The teacher is going to show you how to determine sum of different shapes, you know, so on and so forth. Exactly. The area of triangle ABC actually equals to 1 over 2 C times A, right? That one will be the 3 trapezoid plus the little triangle in the middle. I'm going to write it out. C over 3 times 2. B over 3 times 2. A over 3 times 2. Plus the little one in the middle, 1 over 2, 9, AC. Right? This is an equation you can do a quick simplification. This is not a rocket science. AC equals to 3C plus 3B plus 3A. Okay? This is nothing florid. Now you have one equation, 3 variables. Of course, you can't really solve it, right? Is there some other relationship between ABC? Can I find out some other equations? Or that's it. That's everything I have. Some other relationship between ABC? Paul?
Just a Pythagorean theorem.
Exactly, right? Pythagorean is given, right? Don't forget Pythagorean. B squared equals to A squared plus C squared, right? So that being said, because you don't really have square here, B is under root A squared plus C squared. Now there's nothing too florid, right? You just basically plug in B into here, right? So you're gonna have what? AC, 3C, 3 under root AC, A squared, C squared, 3A. Which is quite understandable, right? So, do quick simplification, you have AC CA equals to this. AC minus 6C minus 6A plus 18 equals to 0. We talk about it millions of times in our regular lecture. As long as you say this, what is our conditional react? Who can tell me? What are you going to do? This is conditional react number 11. You know, in this lecture, we already talked about 11 conditional reacts. And our entire lecture, we're going to keep talking about different conditional reacts. You're going to use them to guide your thinking in a math competition. What am I doing as long as I say this? Asking for Hansen?
Sorry, Simon's favorite from factoring trick.
Exactly, right? We talk about it millions of times in our regular lecture. As long as you AMC, Euclid, everyone is testing it all over the time, all over the places. You're going to use the Simon's favorite factorization trick right away. So that's going to give you A minus 6, C minus 6 equals to 18. It's very mechanical. Starting from here, all the way just a conditional react. You don't really have to think too much. So now you have two things, multiple them together equals to 18, right? And then the question says everything is integer. A, C, they're all integers. So that being said, A minus 6, C minus 6 is going to share the factors of 18, right? So A minus 6, C minus 6 could be, you just list out all the factors, 18, 1, 9, 2, 6, 3, minus 3, minus 6, minus 2, minus 9, minus 1, minus 18. And you have to keep writing about the other part, minus 18, minus 1, right? Maybe 1, 18, 2, 9. You know, you can keep writing this, right? But because A and C and A minus 6, C minus 6, you don't really care who is who, right? So our conditional react number 12 in our lecture, we keep talking about as long as two items, they're identical to each other, we always going to do what? Without a loss of generality, we can let A is greater than C, right? Because A greater than C, C greater than A, it means there's no difference. The question is not asking the value for A and C. The question is asking what? For how many possible triangles of ABC. So as long as A and C are together, good to go, right? So you can save 50% of your time. Just try to get rid of this other side of the calculation. So you just basically check them one by one, right? So what are you going to do? You check them one by one. These are all the patterns. I'm going to highlight it because this is very mechanical. We talk about this millions of times in our regular lectures. As long as you do such a casework, you can just basically solve it. A can be equals to 24, C equals to 7 for the first case. Second case is 15, 8. Third case, 12, 9. This guy, 3. I think this is like 0. This guy is going to be 4 minus 3. This is going to be 5 minus 12. For sure, these are not going to happen, right? You're looking at A, B, C. They're all positive integers as the side lengths. So therefore, you have 3 pairs of A and C. Automatically, B can be determined using the Pythagorean. So therefore, there are 3 solution pairs. You see? So easy, right? This is a very easy peasy process. As long as you use this easy peasy process, you can figure out this problem. The only thing that you need to know for this problem is at the very beginning, when the question gives you this area relationship, you can't use it. Convert it into side relationship. And from the side relationship, all the following parts, including the Siemens favorite factorization trick, and also without the loss of generality, this we talk about millions of times in our regular lectures, and there's nothing too special. All right, so that being said, we wraps up our lecture number 1. Sorry about that, we're running over time, because lecture number 1, we're going to do a lot of introduction about Euclid, so on and so forth. But like I said, from lecture number 2, everything was going to be 2 hours. So in today's lecture, we actually introduced the first lecture of our 2D geometry, triangles, quadrilaterals, polygons, so on and so forth. These are very important, and these are considered to be the baseline. There are 3 major types of questions you're looking at using the cosine law, using the area compensation conversion, and also the most important thing is similarities ratio is actually you make a perfect square, that's going to be your area ratio. Trust me, all these problems are considered to be the foundation. In today's assignment, I'm going to give you 3 problems, and they're all using the technologies we introduced today, and that's going to help you to do all the problems. All right, so I wish you enjoyed today's open course lecture. So just give you guys an idea how our lecture has been organized, and then I'll see the registered students in our next lecture. So any questions for me? Are we all good? Perfect. If all good, I wish you guys a good day. If you want to have the 100-hour free lectures, you can scan this barcode. If you can't scan her, you can basically took a screenshot. Sometimes there's a limitation. You can't have too many guys adding her for the same day. Take a screenshot, try it tomorrow or day after tomorrow, and then good to go. All right. Thank you, guys. I wish you guys good luck for the upcoming Euclid math competition. Bye, guys. Have a good one.